Okay, it's a pleasure and honor for me to give you an introduction of particle physics in China at this conference. Particle physics in China actually started from Beijing Electron-Positron Collider in the 80s. And afterwards, we had upgrade of the machine in the year of 2003, and then the completion in the year of 2008. You can see from this curve is the luminosity of this E plus minus collider at the energy of 3 to 5 GeV. So starting from early 70s, we had several colliders running at this energy range, and the Chinese government decided at the beginning of the 80s to build the world's largest electron-positron collider at this energy range. So it was a very successful operation, and then afterwards the upgrade went up and continued to lead the luminosity frontier. So actually this research in IHAP now actually lead us to other disciplines like particle physics, astrophysics, synchrotron radiation, spallation neutron source, and so on. So this is the machine operational since the year of 2009, and this is the detector. And you can see that this double ring machine, a so-called factory type of E plus minus collider. The luminosity design was actually the largest ever at this energy range, 10 to times 32. Actually, we managed to reach this design luminosity this year. We have been taking data since 2008, and we collected 1.2 billion J-psi events, 0.5 billion psi prime, and the 3 inverse phantom bar of psi double primes, and so on. So you can see that in this energy range, there are a lot of resonances, and by collecting many data in this energy range, you can study the details of physics in this energy range. A few special important results from BPC2 and the BEST3 is the following. You can see that we observed in the year of 2013 new resonances made by a pi plus minus and the J-psi. So this is a charged charmonium states, and this is actually very important, first of its kind, which could be made of 4 quarks. And so very often it's called tetraquarks. And actually we observed it's a neutral company, and also the excited states of this 4 quark states. We also observed a new kind of light hadrons like X1835, and also the higher energy ones. So you can see very clear particles produced from this energy range. And BEST3 will continue to operate for another, say, 8 years. And by working on this machine, we can study charmonium physics, charm physics, and looking for group balls, precision measurement of FD and FD sub S, and so on. This is actually a large international collaboration. We have 6 US institutions, 13 from Europe, and many from Asia. The future of E plus minus collider for us is actually CPC plus SPPC. For about 8 years, we have been talking about what we can do after BPC2. And thanks to the discovery of the low mass Higgs, a circular Higgs factory actually becomes feasible. So we can build something like 50 to 100 kilometers of tunnel, and then build electron-positron collider in it, and afterwards you can build a proton collider in the same tunnel, just like LEP plus LHC. The science of this machine can be the following. It's a Higgs factory. You can study precision property. You can precisely study the properties of the Higgs, measuring its mass, the JPC, and the couplings, and to look for the physics beyond the standard model, like any new type of Higgs, composite, and so You can study, this is also a machine for the Z and the W, so you can have a very precision test of the standard model of the particle physics, and you can take the factor of 1,000 more Z's than the lab had been taken in the year of 2000, up to the year of 2000. It can also be a flavor factory, and afterwards in the same tunnel we can build a 100 TeV kind of proton collider, and we can do direct searches of new physics, and this becomes a precision measurement and a new physics searches. So it's actually complementary to each other by having these two machines in the same tunnel. So actually a lot of people question why you need to build such a large machine. What if you see nothing? And what you can learn from after the Higgs. So actually I think it's a belief by most of the particle physicists that the standard model is not the end of the, it's not at the end after the discovery of the Higgs. So we have the issues like the hierarchy problem, because the elementary particles had a mass difference by a factor of 10 to 13. And you have a fine-tuning problem that the Higgs mass should be cancelled by each other at such a precision, and it's very unnatural. And the mass of Higgs and top quark mass are at the metastable region. So you have an instability region and a stability region. Higgs and top mass are right at this middle here. So this is actually very, very strange. And at the high energy, standard model give you that the couplings do not coincide at the same point, while a minimum supersymmetric standard model give you this kind of interpretation for the unification of the couplings. Also, in the standard model, we have no dark matter particles, and in the standard model, we are not able to explain matter-antimatter symmetry in the universe using the known CP effects. So many of these issues actually relate to the Higgs and relate to the mass problems. So by building a Higgs factory, you can study very precisely the Higgs physics, which means that you can probe with the precision of 1%, you can actually probe to the mass at the level of say 1 TeV, and this is actually is a factor of 10 better than the Large Hadron Collider at CERN. So this one shows you the precision at CPC. Typically, we can do a factor of 10 better than LHC. And this to give you the relative error. You can see a factor of 10 improvement across almost all the parameters. And in particular, this Higgs-Z coupling can give you actually 2 orders of magnitude improvement. Having this precision on the Higgs-Z couplings, you can actually study the nature of the electron-weak phase transition. So we all know that the first order or second order phase transition is not yet known, and they have profound implications to the cosmology. And at CPC, first we can do a direct measurement of or indirect measurement of the Higgs self-couplings with a precision of 20 to 30%, shown here. And this 20 to 30% can give you roughly a 4 or 5 sigma kind of 4 to 5 sigma kind of determination of the self-couplings. And also with Higgs Z couplings, the CPC with roughly 0.2 kind of precision, you can actually discriminate all the models. So this actually gives you all the physics. You can do also the electron-weak determination of the new physics, and this is CPC, and this is the current understanding. A factor of order of magnitude improvement is expected. You can also looking for new physics at the order of say several TeVs by having this CPC machine. You can also do direct searches at 100 TeV machines, and actually for naturalist issues, LHC can give you 10 to minus 2, and the new SBPC can go up to 10 to minus 4, fine tuning issues here. So we finished a conceptual design report with several hundred authors from all over the world. And this is the design of the machine that you can build from LINAC and then a booster, and then you have a storage ring so that the particles can collide. This is a very innovative design for the machine. Instead of building say single ring machine or double ring machine, which had already examples in the world, we invented a new kind of machine which is called partial double rings. So by doing this, you get all the advantages of say less difficulties, higher luminosity, but with lower kind of cost. So this is the so-called double ring machine design with the luminosity. So if you build say 100 kilometers, and you can actually have with this partial double ring machine, you get the luminosity which is the same as the full double ring machine as designed by CERN. So we have the same luminosity if we go to the same circumference. So of course there are many technical challenges. I'm not going through the details, but I think the R&D effort has been started, and we believe that in the next 5 years we should be able to resolve all the technical issues. A few main candidates of the site, either in Qinhuangdao in Beijing, nearby Beijing, or in Xi'an or in Guangdong. This is the design of the civil construction, and the cost is roughly a quarter for the civil construction, and the rest is for the machine. Rough timeline is the following. We hope that we can start the construction in the middle of next century, say the next decade, say 2022 to 2028, and then the SPPC will start in the year of 2030 something, or even 2040. The current status of the funding is the following. So we finished the pre-CDR. We are working on the conceptual design report, and we are asking actually funding from our government. We got some funding from the Institute of High Energy Physics. We got approved by the Ministry of Science and Technology for 35 million RMB, and also another 40 million will be asked next year. We believe we should be able to get it. And then we failed to get the funding from National Commission for Development and Reform this year, and this is during the voting process. We didn't get enough vote. But we believe we should be able to get some other fundings from CAS and the National Science Foundation this year or next year. We are working on the international collaboration. We believe we need a new kind of format for the international collaboration. So it's not ITER, CERN, or IRC, and something which we have to invent. We established an international advisory board. You can see many of them actually sitting in this room. And we already signed many MOUs, and also have official meetings with funding agencies in many countries in the world. And we signed an agreement, and we are going to work together towards the design of this machine. And also we need international coordination for this effort. Okay, so major effort for the high energy physics in China actually is summarized in this table. So we have X-ray-based particle physics program, the best three, and the future is the CPC. We have working also projects working at CERN. We have underground experiment like Daya Bay, Jinping Underground Laboratory experiments. On surface, we have a cosmic ray experiments. In the future, we have LASO. And in space, we are members of AMS, and also a few satellites now in space. And in the future, we have a few projects under planning. So this is a new experiment we are going to build in Sichuan. Sorry, this is a little bit wrong. So it's somewhere here. In Sichuan province, with an altitude of 4,300 meters above the sea level. And this is the design, and the construction has been approved by the Chinese government. And you can see that this is sensitivity of LASO for the gamma astronomy, and this is a CTA. So you can see that at the high energy, we are actually the best in the world, and the low energy, we are able to compete actually with some of the existing and also future projects. So the construction will be finished, I think, in the next by probably 2020. In space, we have many projects. Like we are a member of AMS. We are going to launch 2 satellites this year. One is called the Polar for the gamma ray polarization, and another one for the X-ray astronomy. Actually, we are planning for a new experiment in the Chinese space station to be launched in the year of 2023. You can see from this table the existing satellite or space station experiment and the parameters. Here is what we are proposing right now, and you can see that the acceptance particularly is almost factor 10 higher than the existing experiments. So actually this is the so-called the next generation experiment in space station is going to supersede all the other experiments currently and the planning already in space. So the collaboration, international collaboration has already built by groups from China, Italy, Switzerland, Sweden, and so on. The acceptance at the high energy will be the highest in the world by that time. In Jinping, we have a world deepest underground laboratory with overburden of roughly 2,400 meters. Currently, there are 2 experiments. One is xenon-based Panda X experiment. Another one is the germanium-based CDEX experiment. Both are looking for the dark matters. For the future, the infrastructure construction has been approved, and the next generation xeno or germanium-based experiment is still in the planning, either for the dark matter searches or the double beta decay experiment. This is the very recent Panda X result. You can see that they got almost the best results in the world. And there are people also talking about future experiments there. For another class of underground experiment are the diabase neutrino experiment. You can see this is the planning of the plan of the experiment with the near detectors and the far detectors, and this is a picture. The idea was proposed in the year of 2003, and the results was obtained in the year of 2012. This is a large international collaboration with 16 institutions from US and many from Asia and 2 from Europe. Actually, we are now building a new experiment called Juno. It's actually, again, the reactor neutrino experiment, which looks at the 2 reactor neutrinos from Taishan and Yangjiang, with a baseline of roughly 50 kilometers. So this 50 kilometers of baseline is put you a detector right at the oscillation maximum of theta 1,2. So by having a detector right at this oscillation maximum, you can study the neutrino mass hierarchy. So we plan to build the world's largest liquid scintillator detector with a diameter of roughly 35 meters. So this 35 meters of acrylic tank is going to house 20 kilotons of liquid scintillator. So this is, I don't know, 15 something of meters of diameter. So 35 is factor 3 larger than this hole made of 10 centimeters of acrylic. So this is actually technologically a very difficult and a big challenge for us. So the physics with such an experiment is follow. You can do the mass hierarchy, determine the mass hierarchy in 6 years at the level of 4 to 5 sigma, and you can do a precision measurement of mixing parameters. You can see that with Juno, you can improve almost by a factor of 10 and get, say, sub% level of precision. And you can also do many other things like supernova neutrinos, geoneutrinos, and stellar neutrinos. So the current schedule is following. We already started the civil construction last year. So the civil will be completed by end of next year. And then we start the detector installation. And by year of 2020, we can start the data taking. So this is our preparation, and this is the tunnel digging still ongoing. This is again a very large international collaboration. We have 27 institutions from Europe, and many from Asia, and from America, and so on. We have now already more than 400 collaborators in this experiment. So actually, Juno has a long, has a long future. We are able to insert a balloon into the Juno detector and fill the balloon with a xenon-loaded liquid scintillator. So by doing this, we can build the world's largest detector for double beta decays. So you can see the sensitivity as a function of the fiducial diameter, and our detector diameter is 35 meters. So we can easily put, say, 8 meters diameter or even 18 meters diameter balloon into the detector, and having, say, a fiducial mass of 50 tons. By having 50 tons of fiducial volume, you can see the Juno double beta decay experiment can get the world most sensitive determination of a neutrino effective mass of double beta decays to the 5 to 15 milli eV, much better than these are all the experiment and the planning. I mean, all the existing one is at the level of several hundred kilograms, and the future one is few tons, and we are now moving towards 50 kilotons for the planning. So these are the planning of the Juno experiment, and in summary, I again put this table, and you can read it by yourself. So thank you.
Can you tell us any more about the process for site selection for CPPC?
We haven't finally decided this. We still have to negotiate with the local government, and I believe we have to wait until the government approval officially of this project, then select officially the site. So at this moment, it's just probing the offers by the local government and see which one is the most suitable for this project.
Any other questions? If not, let's thank the speaker here.